9-6 is graphs of polar equations. If you have not already gotten these notes open, you need to get them open. So we are going steps further than just plotting polar coordinates, right? If 9-5 was plotting a polar coordinate, if I gave you something like 3, 5 pi over 6, you would be able to plot that individual point. Now we're going to start to make shapes from those points because we're going to start to get equations. This is your polar graph with added in, like you'll see this if you Google polar coordinate grid. It adds in like a pi over 12 and 5 pi over 12. It adds in all those, like all the over 12s. It adds them in, which sometimes just means that you be plotting points that are a little bit more accurate, but everything else is the same. So if I gave you a point that said 2, pi over 12, you would just find that pi over 12 line, go out to the second ring and plot your point, okay? So it could give you more lines, but at the bare minimum, you would still be plotting the things that we plotted before, like the pi over 6. The over 6s, the over 4s, the over 3s, the over 2s, and then the whole numbers like all the way around, okay? So the way we'll plot this first one is the way I would say to plot anything you don't know what it looks like, and that is by plugging in points. So we are going to go through the work, and this is a tedious process because there's so many of them. We're going to go through the work of plugging in these points. And then I'm going to teach you a bunch of shortcuts and things to check for so that you don't have to plug in all of these points. There will still be times in which you're plugging in points, but not nearly this many, okay? So we are going to take and we're going to plug in those angles into our equation, which says r equals 4 sine theta. And these are thetas. So I'm going to take r equals 4 sine of 0. And hopefully by this point we're getting really familiar with our unit circle because all of those are unit circle angles. So if I pull it in just so we have the visual, obviously it's important for you to know this. But I'm going to pull this in just so you have the visual. Wait for it. I would say you would want to know the same amount of information you knew for the quiz, which was the radians and the coordinate points at these. The good news is that you won't see like tangents. You won't have to do that kind of stuff for these types of graphs. All right, so at 0, the angle that is 0, the sine, so the sine we're looking for the y coordinate each time for this one. So the sine there is 0, so this would be 4 times 0, which is 0. So my coordinate point there is 0, 0. Then I go to the next one. R equals 4 sine pi over 6. At pi over 6, my sine is 1/2. So 4 times 1/2 is 2. Then I go to the next one. R equals 4 sine pi over 3. This is 4 times root 3 over 2, which is 2 root 3.
Are they all going to be positive?
No.
Like these that we just did are all in the first part
So far,
right?
yeah. And just for this one, that could change. All right, so then R equals 4 sine at pi over 2. At pi over 2, my sine is 1. And then I keep going. R equals 4 sine 2 pi over 3. At 2 pi over 3, my sine is root 3 over 2. Five pi over 6, my sine is 1/2. Sine at pi is 0. Seven pi over 6, it's negative 1/2.
Is that a 7 pi over 6?
Yeah. 4 sine 3 pi over 2 at 3 pi over 2. Sine is negative 1. 11 pi over 6. Sine is -1/2. And last but not least, 4 sine. 2 pi, sine at 2 pi is 0. So again, once I teach you about symmetry and about the specific kinds of graphs, we'll never have to plug in that many points again. If you had no idea what a graph looks like, so this is kind of like when you come to the test, if I don't know what it looks like because you forget about symmetry, you forget about the points that we're going to kind of, like, there are specific different kinds of polar graphs, then you can always fall back on plugging in points. It's just total time waster, okay? Not to say you won't have to plug in some points. You will have to plug in some points, but you wouldn't have to plug in all of those. All right, so now we're going to graph each of these. So this would be my r and my theta. So this would be 0, 0. So at 0 degrees, I'm going 0 radius, which means my point is at the pole. The next one would be 2 pi over 6. So at pi over 6, I go out to the second ring. Then I get 2 root 3. We're going to graph this, which means we have to approximate it. Like root 3 is like a 1.8, 1.7. You could totally approximate it. Times 2, and that's 3.6. So we're going to say this is pi, or 3.6. Pi over 3. So at pi...
The pi over 3, does it go for, oh, it's r.
Yeah, it's r first. Pi over 3, and this is 3.8, or 3.6. Good morning. And then I get 4 and pi over 2. Thank you. So at pi over 2, I'm at 4. Two root 3, again, that's 3.6 that we're approximating, and 2 pi over 3. So at 2 pi over 3, we're going 3.6. 5 pi over 6. I go to 5 pi over 6. I go to 2. 0 pi. I go to 0, or pi, and I go to 0. So again, it's at the pole. Anything with a radius of 0 is at the pole. -2, 7 pi over 6. So this time, I'm going to 7 pi over 6.
You just re-went to the center for...
Yeah. God bless you. So 7 pi over 6 is all the way down here, right? Over here. But it's a -2, which means I point away from that line, and I'm actually going to the coordinate point that I already have. So if you think about your sine and your cosine curves, and when we graph them, those curves are all repetitive, right? Just like if I keep going around my unit circle, the same values keep happening in a cyclic form. The same thing's going to happen here. As soon as you start to double back around, it should continue to double back around. So I already repeated the 0 point. I already repeated this where it's at +2 now, but it was -2, 7 pi over 6. The next one is -4 and 3 pi over 2. 3 pi over 2 is at the bottom, but -4 tells you go up to the top. And then -2, 11 pi over 6. 11 pi over 6 is over here, but I'm going negative, so it's back of a duplicate point that's already there. 0 and 2 pi, anything that's got 0 is at the pole. So I have duplicated points, which is totally fine. It should happen at some point. It may not happen in the range that you plug in all of the time, but if you have a wide range like this, it's going to duplicate. So what I've actually done is drawn a circle with these points. So we are going to learn how to graph much easier than this. A circle, something called a lemison. Yeah, I know they have weird words. A rose, which are pretty. And what am I missing? A lemniscate. I was like, there's 4. A lemniscate. Yes, it looks like an infinity symbol.
It's not really supposed to be a perfect circle, right?
It actually should be a perfect circle if we had plotted all the points in between, but we didn't plot all the points in between. Like if I had plotted a point on pi over 12, it should have given me a perfectly rounded circle. So you're going to learn just by looking at this equation that is a circle, and then you're going to learn what it's symmetric to, and then you're going to save yourself a crap ton of time of plugging in points. If you don't learn those things, then this is your future, plugging in a crap ton of points, which you don't want to have to do, okay? But you can always fall back on it. Questions before I move on? Well, it's all right. All right, so one of the things that we're going to learn about that's going to help us with these graphs and to eliminate all that extra work is symmetry. There's 3 types of symmetry with polar equations, just like everything else. There's 3 types of symmetry. We used to have y-axis, x-axis, and origin symmetry. We don't call it the y-axis, we'd call it pi over 2. We don't call it the x-axis, we call it the polar axis. And we don't call it the origin, we call it the pole. But it is exactly the same thing. So something that is symmetric with respect to the pi over 2 line, which is what we just graphed, that was symmetric to the pi over 2. All the points that happen on the right happen on the left. So you can eliminate half of your points by knowing that they duplicate over the y-axis or the pi over 2 line. If this was a cosine graph, so if it said r equals 4 cosine theta, then it's actually symmetric, 1, 2, 3, 4, to the pole. The polar axis, sorry. So I would know that. I would only have to graph what's in the first quadrant, and then I can reflect it down into the 4th quadrant and save myself literally half of the plugging in of the points. Yep. So the first one is symmetric to the y-axis, right, which we call the pi over 2 line. So I would have plugged in these points, and then I would know immediately reflect it over the y-axis or over the pi over 2 line, and I get the other half of the circle without having to plug in points. Like flip it over the y-axis or reflect it over the pi over 2 line.
How do you know when to stop? Like when you're done doing one side of the circle?
Once you've filled the first quadrant.
Oh,
Yep. Then the same thing would happen if it was cosine. It's going to be symmetric to the polar axis. So I would find all the points in that first quadrant again, and then I would flip them over the polar axis or the x-axis. So you're eliminating half of your points by knowing symmetry.
the first part is when it has pi over 2.
If it's symmetric to pi over 2. So it may not have pi over 2 in it. I'm going to show you. It's like I think on the next slide. You're looking for sine.
And then that one has cosine.
Correct.
Oh, and the origin one?
The origin is only going to happen with an r squared, or if both of these things happen, which you're never going to see something that says sine cosine, not anyways in here, okay? Like it's not going to say r equals sine theta cosine theta. That does not happen. But you are going to see something that says r squared.
How would you flip it in respect to the pole?
Whatever happens here, we flip here. So you use the same angles, but the opposite r.
And it makes
It's called a lemniscate. It's an infinity symbol. So a circle with a center at 0, 0, like what we've graphed already, like if it has a center at 0, 0, then it has all of these. And that's the only time that you'll see all of them, like from the equation, if it just said r equals a number. Like if r equals 4, this is a circle with a center at 0, 0, and a radius of 4 in each direction. Wait, that's 3. So that's the only like simple one in which you don't have, there's not even anything to plug points in. You know that you are going of a radius of 4 in all directions, right? So that would have symmetry to the pole, to the pi over 2 line, and to the and to the polar axis. That and a rose that's in each quadrant, which we'll get to those later. But something like that would also be symmetric to all 3. Most of the time it's one of them, but there are times in which it overlaps. So this is like the official test for symmetry. If I wanted to actually test to see if my graph is symmetric to the pi over 2 line, then I would take my original coordinate point, whatever r theta is, and I would change both the r and the theta. If I make the r negative and I make the theta negative and it gives me the same point, then I would know, and then it gives me the same equation, then I would know it's symmetric to the pi over 2 line. If I'm doing the test for the polar axis, then it is the change of just theta. You can also do negative r and pi minus theta, but that's so much more complicated. So you just have to change theta. And if it's symmetric to the pole, then look, r theta, we just change r. Those are the official tests, though. There are shortcuts I'm going to teach you, okay?
The first one was both.
The first is both, so pi over 2 is both. Polar axis is theta, becomes negative theta. And pole r goes to negative r. So if I had my equation and I plugged those in and it goes back to my original, then it's going to be symmetric to whichever one that is. So it's because of your even and odd, which is next. Because of your even and odd tests, this is basically just what it said. So replace r theta with, I would do both. I think that's easier than the pi minus theta for the pi over 2. For the polar axis, replace r theta with r negative theta. And for the pole, replace r theta with, and I would change the second one, negative r theta. But again, I'm going to teach a shortcut. So if you forget the shortcut, then that is how you do it.
Are you going to give us an example of how it would look? Like with how it's or
Yeah.
like,
You mean like how to reflect it
like how to tell when
from the equation?
Yeah.
I'll show you once though, but then I'd rather you use the shortcut. But I will show you. So these are the shortcuts, okay? No, sorry, this is the quick test. So it says, which is a shortcut, but because these even and odd properties, and this goes back to like our trig identities, because tangent is odd, which means if I change the sign on the angle, it actually will change the sign on the value. But cosine is even, which means that even if you change the sign on the angle, it does not change the sign on the thing. Then these quick tests are for 'em. If your equation has sine in it, it is symmetric to the pi over 2 line. So think sine is your y coordinate. The y coordinate, it's like the y-axis. That's what it's symmetric to. If it has cosine, then it's symmetric to the polar axis. And again, think cosine is like your x, and the polar axis is like your x-axis. You cannot use these for the origin test. Okay, but you can use them for the pi over 2 and the polar axis.
pi over 2 is your y-axis.
Pi over 2 is your y-axis, which is why it should make sense that sine would give you that symmetry. Okay, so now let's use that together with plugging in some points to figure out this graph a little bit easier. So first of all, by looking at my equation, which trig function do you see? Cosine, which tells you symmetric to the polar axis, which means everything that happens on the first and second quadrants can get duplicated down to the third and fourth quadrants. So I'm only going to plug in 5 points. I'm going to plug in 0. I'm going to plug in pi over 4, pi over 2, 3 pi over 4, and pi. So I would say by rule of thumb, the quadrant angles are important, and then at least one. There are going to be times when you need more than one, but at least one from each quadrant. So I'm going to take and plug them in. Oh, so the rule, so the test for symmetry, and I don't want you to do this all the time because I think it's easier to use the shortcut. But if I take in here and I plug in any kind of positive angle, right? Cosine is going to give me a positive value here. Like, let's just say I did pi over 6. Cosine at positive pi over 6 is root 3 over 2. Now, if I took and plugged in negative pi over 6, which is here, cosine is also positive root 3 over 2. So the angle, when the angle is negative on cosine, it's like it doesn't even matter. It goes back to positive. So that's why it's a test. But because it's even, only cosine is even like that. So the cosine at 5 pi over 6 is the same as the cosine at negative 5 pi over 6. Does that make sense?
Even though technically...
No, they are. The value is the same because it's the x. So the x is always going to be positive on this side. Doesn't matter if I'm here or here. And the x is always going to be negative on this side. Doesn't matter if I'm here or there. It doesn't work for the y because here the y would be positive and here the y would be negative, which is your sign.
Also, how did you know that it was going to be the first two quadrants?
I don't know. I'm just going to plot the first two quadrants and then I'm going to reflect it. I could have plot 3 and 4 and then reflect it up. It doesn't matter. I just know it's symmetric to this line.
But you know to plot either the first two or the third and the fourth because
If it's cosine. If it's sine, it's going to be symmetric to the polar axis.
Right.
So I'm going to plot these two or these two and then flip it over. Did I answer your question?
Yeah.
Yeah, okay. All right, so let's plug them in. So r equals 3 plus 2 cosine at 0. And the cosine at 0 is 1. This coordinate point is 1, 0. So this is 3 plus 2 times 1. 3 plus 2, which is 5. So my coordinate point here is 5, 0. Remember, radius comes first. Wait, you both asked a different question at the same time. What? I plugged in 0. I said I was going to plug in 0, pi over 4, pi over 2, 3 pi over 4, and pi. You need, the quadrant angles you want to plug in, and then I said 1 from each quadrant that we're plugging in. There are going to be times, and as we get more comfortable with these, you'll understand that. There are going to be times in which you plug in different ones, but for now we're going to plug these in. I plugged 0 in here, so that was my first angle. So now 5, 0 is here. Now I'm going to go to the next angle. R equals 3 plus 2 cosine pi over 4. 3 plus 2, the cosine here, this is root 2 over 2 and root 2 over 2. Root 2 over 2. This cancels. I'd get 3 plus root 2, which we're going to approximate to be 1.4. And this becomes 4.4. So this is going to help you later, but root 2 we approximate to be 1.4, and root 3 is like a 1.7, but there's times that I make that 1.8 just to make my life easier so it's even, I'll be honest. But you're going to use those a lot. Like it is 1.7 approximated, but if it's over 2, I tend to make it 1.8 so it divides evenly. You're never going to get more accurate than that, so it doesn't matter. Yeah. Oh my word. Okay, so now that next coordinate point is pi over 4 and 4.4. So pi over 4, 4.4 is like there. Then I go to the next one. R equals 3 plus 2 cosine pi over 2. The cosine at pi over 2 is 0. So 3 plus 2 times 0 is 3. So 3 pi over 2 would be that coordinate point. Then I plug in 3 pi over 4. Coordinate point here is negative root 2 over 2 and root 2 over 2.
Wait, did you already plot 3?
Yeah, that's the one at pi over 2 at the top. So this is 3 minus, we're again approximating that to be like a 1.7. So this is 1.3. Which is there. And then the last one we're going to plot by plugging in is pi. Coordinate point at pi is negative 1, 0. 3 plus 2 times negative 1. 3 minus 2, which is 1. Square root 3?
No. This is
Square root 2, we I did it as 1.7. This should be 1.4. This should be 1.6. Yeah, that should be 1.6. Not that it makes much of a difference, but yeah. Yep. By knowing it's symmetric to the polar axis, I can now take all those points that are above my polar axis and reflect them down below. So this coordinate point that is at 3 pi over 2 and what is that, 1.4, I'm going to reflect down to 5 pi over 4, 1.4.
Wait, which one did you reflect?
I'm doing the 5 pi over 4 one first. So 3 pi over 4 reflected down to 5 pi over 4. Then the pi over 2 one was at 3. So pi over 2 at 3 reflects down to 3 pi over 2, 3. So this point got reflected here. And then the pi over 4 point would get reflected down onto 7 pi over 4. No. It's not a circle anymore. This is called a limison. It's like a shape with a side smashed in, which again, we're going to figure out in a second. But if you didn't know anything, I went on the outer, I didn't go far enough out. Hang on, sorry. It should be here. Okay. So if you have no idea what your graph looks like, which again, we're going to learn the names of these graphs and the overall shapes of them, all I would do is just connect these points. And it makes this weird shape like a circle that's been smashed in. Okay, that shape has a name.
I think I'm missing. Wait,
You should
why
have,
did you reflect the 0?
because it's on the, so you can't, like where's this going to go? What's symmetric to this?
The other side.
No, that would be over the pi over 2 line. We have to do it up and but down.
Oh,
Yeah.
right.
So if it was sine, we would have done that.
Oh, okay.
It's all right. They're going to get better. I promise.
So it's just a circle.
It's not a circle. It's called a limison, but it's like a circle with a side smashed in.
So the cosine is telling you to make it symmetric to the x-axis?
Correct. All right, so remember I said there's 4 types. This is the first. It's called a limison, okay? The way you identify that something is a limison from the very beginning is by having a plus or minus in your equation. So your trig function, which could be cosine or sine, doesn't have to have, like the b could be 1. It doesn't have to have a number in front of it, but it is going to be something plus or minus cosine of theta or something plus or minus sine of theta. Now, this doesn't mean that the plus or minus can't come after, because this would be the same thing if it said b cosine theta plus or minus a. Anything that's separated out by a plus or minus has this shape, which is called a limison. It looks different. So within the limison, there's 4 different shapes. The first is a limison with an inner loop, and it literally has a loop inside its graph.
That will show once you're plugging.
It will, but you'll want to know it before you even start to plug things in. So you're going to learn these tests so that before you even start to plug points in, you'll be able to say that this is a dimpled limison. And then from there, you'll know what your graph should look like. Then you're going to plug in points to back up your...
So basically, we kind of have to memorize those things
Yep.
to know what...
Yep. So with a limison, there's 4. The first is the one with the inner loop. The second is called a cardioid. It is a heart shape. It literally goes in with like a sharp point like that. And the third is called a dimpled limison. It looks like a kidney bean. It comes in just a little bit, but more as a curve instead of a sharp point. And the last one is called a convex limison, and it has a flat side. So the way I think we've talked about this before, but I'm a visual person. I remember this slide. And every time we talk about limisons, I will come back to this order. So I think about it starting as a circle on the right, and something is pushing it out this way. No, other way around. Something is pushing it in this way, and it's causing less and less and less. So this is flat. All right, so it is flat, then it comes in a little bit further, then it comes in a little bit further, and then it comes all the way in and does that loop. So if you remember that pattern, then the things underneath here should make sense, right? So the way you decide if it's an inner loop, a cardioid, a dimpled, or a convex is the relationship between A and B. A is the number that is by itself. B is the number that is attached to the trig function. So whatever's being added or subtracted separate, that's your A. And then the B is the one that's literally attached to the trig function. If A over B is less than 1, then it's got an inner loop. If A over B is equal to 1, then it's a cardioid. If A over B is in between 1 and 2, then it's a dimpled limison. And if A over B is greater than or equal to 2, it's a flat or convex limison. So if you look at the one we just did, first of all, I would know it's a limison because there's something adding or subtracting to my trig function. That something added is the A, so A is 3. The number on the front of my trig function is B, and that's 2. And 3 over 2 falls in between what? It falls in between 1 and 2, so this would be a dimpled limison. So if you now know that going into it, then you know that when you go to graph this, it should make a more fluid shape on one of the sides. So when it comes time for test and you get a limison, you're going to have to figure out what kind of limison it is and then graph it. So it would be classify it. It would be classified as a limison. Then is it dimpled? Is it cardioid? Is it convex? Or is it inner loop? And then plot your points. And R equals, and it said 2 plus sine theta. How does this change the classification?
It's 2 over 1, right?
So that's,
This would be 2 over 1.
that's the last one. It's the one, that's that one.
This would be a convex limison, so it would be more flat here on the side. And it's not going to be turned this way at all because it's sine. It's going to be to the y-axis. So it's going to be like a flat, almost like that. Or it could be turned the other way, depending on the signs.
But the flat would either be on top or on the
Correct. So on the axis that it's symmetric. Right, because if you put it here, like if you think about this, this is not symmetric to your y-axis, right? It would rotate. This would be symmetric to the y-axis. I mean, it's horrible drawn, but you get the point. Yeah. So as soon as you see something that's separated with a plus or minus, then you're going to know that that is a limison, and then you're going to classify it as cardioid, inner loop, all that stuff. I mean, you're going to have to tell me if it's cardioid, like that kind of thing. Like, I'm not going to mark it wrong if you spell it wrong, if that's what you're worried about. Yeah, no. Okay. The next one is a rose. Okay. These are pretty. Yeah, they are pretty. These are my favorite. Yeah. So a rose has petals on it. Okay. These petals are those loops. So you will identify that a graph is a rose based on the equation having something next to the theta. So this is how we know that that's a rose. It would say something like R equals 3 cosine 2 theta. Or R equals 3 cosine 5 theta. Something like that. The number is in between the trig function and the theta. Now R is still raised to the first power because this is going to change when we get to the limnoscates. Like R would be squared and there's a number in between. But if R is raised to the first and there's a number in between, it's a rose. If that number is odd, then that equals the number of petals. So odd equals the number of petals. If the number is even, then you double it to get the number of petals. So if it's odd, so if n is odd, there are n number of petals. If n is even, then there are 2n number of petals. So there will never be a rose with 1 because then that would just be a limison because there'd be no number there, right? The smallest it can be a 2 theta, which means the smallest amount of even petals would be 4 even petals. And then if it's a 3 in between there, then there's 3 petals. But there's never going to be less than 3 petals, okay? That becomes a limnoscape. So that's the first thing we want to identify. It's a rose, how many petals it is. Then the number on the front of it is the length of the petal. So that's the furthest point out. So A is the length of the petal. Then you want to look for symmetry. So this could still be symmetric to the polar axis, like this one's symmetric to the polar axis. Whatever happens above it happens below it. It could also have symmetry to the pi over 2, which is like this, right? That would be symmetric to the pi over 2 line. Or it could be both, like this one, where that's symmetric to the pi over 2 line. It's symmetric to the polar axis. It's also symmetric to the pole, okay? So if it's got an even number and it's like on the axis like that, then it would be all of the symmetries, okay? So then the goal is to figure out where's the longest part? Where does that occur? And I'll show you 2 different ways to do it. You can either like plug it in and test it out, or you can work backwards. And then that gets you the furthest point out, and then you literally just want to find a couple other points to bring it back in. So a rose to me is one of the easiest to graph because you know what the shape looks like. You just have to figure out where the petal ends, okay? The circles, I'm going to come back. Okay, so this is the rose. I know it's a rose because there's a number in between the trig function and theta. So it's a rose. How many petals does this rose have? 4 petals. Does it have symmetry?
Where did you get the 4 from?
Because if it's even, it's 2 times it.
Oh, so the second number.
The number in between, yep. Does it have symmetry? What's our quick test for symmetry? If the trig function is cosine, it's what?
Polar.
Good. Symmetric to the polar axis. And the other thing I know straight from my equation is the length of the petal, which is how long?
2.
Good. So I'm going to pull in a polar graph. So if it's symmetric to the polar axis, I want to plug in first, second quadrant and then reflect it down. More importantly than that, I want to be able to find where these petals occur. So there's 2 ways to do this. One is start with your quadrants, plug them in and see if you get 4. So if I start with 0, let's say, I would get r equals 2 cosine 2 times 0, 2 cosine of 0. What's the value at 0? I mean, what's the cosine at 0? 1. This would be 2 times 1, and that's 2. As soon as I find r of 2, I know there's a petal there. So the furthest point out here is 2, and I put a petal.
Oh, so you ignore the number that's like cosine 2, 0?
Well, only because it's 0. If I plug in...
Oh, yeah, because, so you multiply.
So if I plug in pi over 2, which would be like the next one I would do, these would cancel. I'd get 2 cosine pi,
Okay.
and then the cosine at pi is -1. This is -2. So that's telling me at pi over 2, I'm going opposite direction. -2 puts my other petal there.
Okay.
With me so far? So now if I plug in the other quadrant angle, which is pi, I'm assuming there's another petal there because this is symmetric. So 2 cosine 2 times pi. Cosine at 2 pi is 1, and there's another petal.
Are they all going to be the same length?
They have to be 2. Yeah.
So can't you just go up 2, 2, 2?
Yeah. If you know your symmetry, that's all you got to do. Yeah. Yeah, I think the rose is the easiest. If you can find the petal. Sometimes the petal's like over here, and then you've got to know that it does that. So you just got to know your graphs and find the petal. So if I didn't find, well, and there's one more, right? Because I need 4 petals. Where's it going to be?
Up top.
Up top. We didn't get it at pi over 2, though. How else would we have gotten that point? Because when we did pi over 2, we got a -2.
3 pi over 2.
So let's try 3 pi over 2. What do we think is going to happen? Three pi is here. It's a -1. So it's 3 pi over 2, but negative gives me that fourth petal, okay? So it should be consistent.
Do we have to show our work like that? Or
No. So when you get if you get a rose, you got to find me one petal and show me symmetry, and then you're good. I would say I would probably check maybe 1 or 2 other points, but you don't have to go through plugging in all of them. Some of these roses are going to be in the quadrants. So you could have one that falls on the pi over 2 line, or the pi over 4, or the pi over 3. You might have to do a little bit more work to get those, but you can find it. So we plugged and checked. The other way to do it is if I want to get a petal of 2 length, I can do this and work backwards. So I can say what theta is going to give me a radius of 2. So I make r the petal length, and then I would divide both sides by 2. This is 1 equals cosine 2 theta. I'd be asking myself, where on my unit circle is cosine 1? And what's that answer? 0. So 0 would equal not theta, but 2 theta, and then I would divide by 2, and theta would equal 0. So I could also find the petal length by working backwards. You can either plug and check, like we did, or you can work backwards by making r whatever your petal length is, and then solving for theta. That works every time.
And that shows that it's symmetric.
That would that tells me that my petal is here, and then because I know it's symmetric to the polar axis, I would figure out the other ones. Yep. So for tonight's homework, and it says it so explicitly, but I want to be so very clear that if you don't graph these by hand, you are not going to get credit for this homework, okay? You have to graph them by hand. There are 2, I think it's 7 and 8, that say use a graphing utility. You can hold off. It's not due till Thursday. You can hold off on those till Thursday. You can do 1, 2, and 3. That's a circle and a limison. One of them you have to distribute, and then let me find you the rows.
When you graph by